So, good morning to everyone, and it's my pleasure to welcome and introduce Professor Podoleanu, I guess, who is a little bit interested in optical coherence tomography. Sooner or later realizes that he is one of the key persons in developing new methods and technologies in this field of new imaging techniques. Last year I was in London, and we took part in a big conference on lasers in medicine, and realized that Professor Podoleanu is a very innovative and open-minded scientist, and therefore I initiated his invitation to our summer school, and I was really happy. That he accepted our invitation. And hopefully this will be the last and first time, because we'd like to go on with this summer school project, and hopefully he can join us next year, and even he can bring some students who are interested in laser physics. So, Adrian, it's your turn now.
Welcome, good morning. Thanks, Professor, for the introduction. My talk is rather technical. I'm an academic in the School of Physical Sciences. We teach physics to physicists, but I also convene the medical physics lecture to our second year undergraduate students. But even so, my language will still be technical. The technology I'm going to present is one which has shown a continuous rising expansion, going from different branches of medical physics and now going even outside medical physics into industry and non-destructive testing. I will refer many times to the acronym of the technology, which is OCT. We are located in Kent, the top of the hill. There are two universities in Canterbury. University of Kent is about Canterbury, overlooking the cathedral and the surrounding. Please come visit, and if you have time, walk 20 minutes up the hill to the optics lab. My lecture is organized along those lines. Technical with applications. I was considering the type of presentations instead of having a lot of images and showing you a large range of applications we do. I wanted to stop on occasions to pinpoint the ingredients of the technology and exactly what determines the focus on the technology, why there is so attention to the technology being given, the resolution achievable, and the speed of imaging, and avenues for expansion. We developed, and everyone working in OCT will be involved in these three subjects, which are something to do with the laser, with the optical source driving the tomograph, optical coherence tomograph, the optical configuration at the basis of the tomograph, and the signal processing being used. And no group involved in this would finish the job unless the technology being created is translated to a clinic and is being used to something. You see here the progress in the number of publications. It's like doubling the number every 3 years. And the fields are more to do, 55% is more to do with something to do with the eye. Ophthalmology, optometry, refractive surgery. If you Google retina or cornea, anterior or posterior segment, glaucoma, AMD, you'll find OCT. And here a list of topics. And I marked a few who are in Kent who contributed with our technology. And you can read by yourselves pharmacology, pharmacy, not only ophthalmology. Before going any further, I wanted to do some matching here. So, as I warned you, I have to be technical. debate briefly of the technology. However, I could slow down on some subjects. If you tell me, for instance, hands up here, how many are physicists? How many have worked with lasers? Medical applications? Okay, thank you. So all these are here. I already prepared the questions. You already answered them. And so the majority are here on yellow. Good. I would also like, if you wanted for me to insist more on some of the aspects, stop me. And I think it's more important to end up with something about technology than going quick through over 200 slides. Now, does anyone have any idea why OCT has been created? It responded to a need. And what was the need which led to the development of technology? Of course, we all needed that, high resolution. However, there was a problem. There was a problem by 1980, the scanning laser ophthalmoscope was invented, 1980, 1981, and that allowed some high resolution of the eye, but that was not sufficient. Okay? So it was a problem to do with imaging with high resolution of the eye, because the eye presented a technical problem to a confocal microscope. We couldn't do any better than maximum achievable because the eye is too long. So, one of the first view of looking at the eye was Helmholtz, 8050, indirect ophthalmoscope. Then, 1980, Rob Webb, Boston, Ice Kaplan's Institute, created the scanning laser ophthalmoscope. However, that's the problem. Normally, with an undilated eye, the undilated eye is how many millimeters? 3, let's say. So it's 3 millimeters, we get something like that. But if you manage to increase the beam diameter, you can make the spot smaller. And we know that from physics, from optics. So here are some calculations. With a normal eye, you will get something like 15 microns transversal resolution by imaging the retina with an undilated eye. However, if you manage to dilate it and use the optics to the maximum, you should be able to achieve better than 5 microns. And now there are specialized systems which achieve 3 microns. In terms of axial resolution, we call it depth of focus. If you use undilated eye, 3 millimeters, that will be about 200 microns to even 1 millimeter. If you dilate it, this would go to 50 microns and even. There are theoretical studies showing it in 40 microns in axial range. However, there is a problem. As we increase the beam diameter, my nice drawings before should be replaced with these drawings. You see, the beams don't focus. We call that aberrations. So that the rays don't go to a defined, nice spot. So as we dilate the eye, we encounter more and more distortions in the beam being projected on the retina. So that is the problem. We cannot take advantage of the geometrical optics by, let's say, fine, we can beat diffraction by increasing the beam diameter and creating a better spot on the retina. That's not possible. So, if that is not possible, you see, there are all sorts of aberrations. There is a theory of aberrations, there is astigmatism, coma, and so on. So instead of fighting with the focus, so we cannot focus because the retina is too far away. It's too far away to focus any better. If it's so far, we need to dilate the eye even more. But even if we dilate it, we encounter the problems from the aberrations in the anterior chamber. So instead of fighting with the focus, engineers devised this method, or let's use a different technology, and that is based on interference. So if we throw as many colors to an interferometer, it's possible to achieve in axial direction resolution which is independent on the focusing power. And that resolution is now determined by how many colors you put into the spectrum. So the larger the bandwidth here, the better the axial resolution. And that's the way the technology has been created. 1991, specialists at Massachusetts Institute of Ophthalmology had the idea of adding a gobble scanner to a low coherence interferometer. And that is the year when the technology took off. Good for macular diagnostic, near histological resolution, and providing, many of you here are familiar with the terminology of B-scan. B-scan like cross-sections in ultrasound. So that is the technology which is being used in OCT. Technicalities now, you see here how we do an interferometer. So you take light from a superluminescent diode, which emits a large spectrum. So the large spectrum, the spectrum being large, is essential for the technology. Divided into two, one to do object under test, OUT, and there is another beam. So that is the difference from a microscope. You add another beam from a reference mirror. You superpose that beam with the beam coming from your object, and you do interference. Or you can do it in bulk, in free space. That green line, you show a beam splitter, you divide the beam into two. So now, when the beam comes back, it goes to the photodetector. And that is the core principle of an optical coherence tomograph. This is also a basic representation of showing the limits of the technology. Now, I'm going to tell you that there are two main types of technology: time domain and spectral domain. Practically, the OCT started as a time domain. But by 2000, 2002, the emphasis shifted from time domain to spectral domain. And I would like to try to explain you, and I would be very happy if you went out from these lectures with this idea, why the technology migrated from this type to the other types. And it's not only that, what are the values of each technology, and what are the applications of each technology. And I'll go back to that. So for instance, this sketch will show you that if you take a beam from the source and you delay some other part of the beam and you superpose them, now if your source has a certain bandwidth, you can associate, and I'm sure physicists here know, you can associate to that a length for the space or for the time. And within this interval, either in space or in time, you have strict phase relations between the waves. So what I'm showing there is a wave train length, and that length is called a coherence length. So now, if you consider that this source emitted a burst of light, which lasted, let's say, a coherence time, and you multiply that by the speed of light, and you obtain the coherence length, the other beam, you see, will determine the same, but when you do the overlapping is not total because it came later. So if I take this mirror and take it down, this wave train will move to the left, so the overlap will be even less. So if I delay this even more, the overlap will be even smaller and smaller until there won't be any overlap, no interference. So it's the wave train length which decides when the image is being created. And it's interesting that this sketch shows the operation of both time domain and spectral domain. For instance, in time domain, this sketch will give you the axial resolution, and in spectral domain, this sketch will give you the maximum operational range of the method. And I'll come back to that later. So here we have a simple description of time domain. You see, the source has emitted that wave train. And because the lengths of the beam going up and the beam going lateral, they are equal, the time taken by the two waves to reach the beam splitter is the same. And they superpose, the waves superpose. So the length here is, this length is equal to this length. So that's why they superpose. However, let's see, now I put the mirror away. So if I start and emit the burst, because this one is longer, when the wave train comes back, it will miss the previous one. So you won't have superposition. Right? So by changing the distance there, I could change the matching condition. I could match the lengths, so I could superpose those two wavelengths. And that is an explanation for what we call low coherence interferometry or broadband interferometry. The first equation is the interference equation, and the third term gives you the fringe pattern. The fringe, and that's what the image is. The image is in this 2 square root of OR, O being reflectivity of the object. But the key is here, because here you have the spectrum, so the more colors you put into the spectrum, that's what I told you initially, by Fourier transformation it will become narrower and narrower, and that is in space. So the more colors, the larger spectrum, the better would be the axial resolution. Because if I go back here, the wave train here will be shorter. So as you put more and more colors, that will be shorter. So now it will be a smaller distance here for this mirror to create a missing situation, and the wave train misses the other one. So practically that determines the axial resolution. That is connected to the length of the wave train. In terms of the overall resolutions, so how do we build velocity? You take a low coherence interferometer. So that fiber or pinhole operates like a confocal microscope, and you will have a transversal resolution given by the focusing power of the microscope. So laterally, the resolution is W determined by the confocal microscopy principles. However, in depth, the resolution and all the operation is determined by the principles of interference, low coherence interferometry. More here. So let's say you take this interferometer is called the Michelson interferometer. You superpose away from the object is away from the reference. And as you move, let's say that you move one of the mirrors away. As you move it, at every half wavelength of that movement, and let's say we work with 1 micron sources. Half wavelengths would be half micron. So if you move the mirror every half micron, you'll get another peak. You move the mirror another half micron, another peak. So I can move that for a mile, and I still get the peaks. So in this case, I cannot use this strategy to provide depth resolved information. So what I need to replace the laser with a low coherence source, i.e. with a source having a broad bandwidth. And in that case, is that wave train length which limits the number of peaks here. So now we can practically evaluate the axial resolution of the method. If you do the Fourier transformation of that broad band, you will find that narrow correlation of peak, and that corresponds to the extension of this yellow fringe pattern. So out of these many peaks repeated at half wavelength, we have here only, let's say, 10 or 20. So you have to replace the laser. If you use the laser, this is what you obtain. You will obtain interference all the time. However, if you put more colors than those colors in a monochromatic laser, your number of peaks will be restricted to the yellow one. So let's say that now we complicated it, and instead of having one mirror, let's place in the object two mirrors. So we have here sigma 1 and sigma 2. This doesn't show very well. Each interface will have the fringe pattern as before. So now you have these two fringe patterns. You eliminate by rectification the oscillation, and you get two peaks. And the amplitude of those peaks will be corresponding to the
there is a pointer isn't there? So
the first one.
very easier to use that.
This one?
Yes.
But this is strong. Stronger. So these interfaces, you see the same fringe pattern as before. You eliminate the oscillation, and you have the peak for each interface. So in this way, by moving the reference mirror here, I could recognize. So by moving the reference mirror, I could recognize the position of this in space. I could recognize the position of this interface in space, and that gives me now the chance to go to the main performance of this technology. I have already alluded to this. So you see here the axial resolution, the coherence length. Is inverse proportional with the bandwidth. The more colors you put into the spectrum, this number becomes smaller, so you have better and better axial resolution. So we work with tens of nanometers to hundreds of nanometers, which determine an axial resolution in OCT which could go from a couple of microns to even some microns. The second parameter is this one. It's about how much light goes into tissue. There have been several lectures yesterday about scattering. Scattering limits the penetrations into the tissue examined. However, here with OCT we have an extra problem. What we wanted photons which are not only returned back, but photons which still maintain phase relations with the photons from the source. So if by scattering, if the phase is lost, even if the photon is back, it's not going to produce interference. So because of that, OCT has a main problem in terms of how much you penetrate in depth. However, if you compare, if you build, take a piece of fiber and build a confocal microscope and use it for skin, and there is a company making that, and if you can Google Lucid in Boston, and you'll see that they quote 350 micrometer penetration in skin. Now, on the same system, add the reference beam, build an OCT now, and do OCT, and you will achieve 1.5 millimeter. So you'll achieve a little bit more because you apply the third parameter, which is here, i.e., according to the interference equation, the signal, the interference signal, is proportional with the amplitude of the signal reflected and amplitude from the local beam. But the local beam is very powerful. So it's like you have here an amplification effect. And that gives us better penetration than the confocal microscope built at the same wavelength with the same system. So these are the three main key parameters of and I still haven't started OCT. This is low coherence interferometer. These are the parameters of a low coherence interferometers. Let's go more. Now we start with OCT. So OCT has been invented by adding means, ways, technical ways to move the beam laterally and do the interference which I presented before. So how do you do that? There are different possibilities. You can, if you put the spot here, now you do the analysis by moving that reference mirror in the interferometer and you get a reflectivity profile in depth, and this is called like an ultrasound and a scan. Now if you put several of these together, if you do many of these, you produce what is called a B-scan, and that's the way the technology started and evolved for more than 10 years. And this is called a B-scan, a cross-section. In Kent, we insisted on this orientation, inspired by collaboration with the Institute of Ophthalmology in London, Professor Frederick Fitzke, who from the very beginning suggested that we look at OCT doing transversal oriented images like those produced by scanning laser ophthalmoscopes. And we call this C-scans, where C, you can take C as standing for constant depths. Okay? Now, you realize that by doing A-scans, you cannot build a constant depth image immediately. There's no way. So that's one problem of a technology based on A-scan, and I'll come back to that. In Kent, we also introduced this other letter in top of A, B, and C, which is T-scans, i.e. when you scan the beam laterally, you produce a transversal reflectivity profile. So that is the terminology of scan. Where the OCT lies in between the other technology, Professor Martin Leahy yesterday had a similar mapping, showing that the OCT is not as penetrating as ultrasound, which could go to centimeters, and not as good as confocal microscopy, which goes to some micron. However, with the recent developments in this called supercontinuum, large, very broadband sources. Now there are extraordinary wideband resources. OCT is now starting to compete with confocal microscopy and being capable of achieving microns and even sub-micron axial resolution. That was one of the first images being produced. That's axial depth, that's lateral. Okay? Compare please with the advance in technology. That is one of our images now, and now that's why ophthalmologists use now in their current practice OCTs, because with an undilated eye, you don't need to dilate it, with power which is safe, less than 1 milliwatt, being sent to the eye, you can get an image with 3 microns depth resolution. This is in fact is an exquisite realization which we published here, where we achieved 3 microns in the leading eye. So now we know all these acronyms, what they mean, and I'm sure there are specialists here who would identify all these layers. Well, so for instance, two parts of the eye which are interesting for our investigations are the macula here, or the photoreceptors are for age-related macular degenerations, and those interested in glaucoma will measure the thickness of nerve fiber layer here with micron resolution to see the evolution of the glaucoma. And you can also do unfast images or C-scan images with the same technology. So what you see here is an instrument which we produce, which delivers 2 images at the same time. It's the old technology here, the scanning laser ophthalmoscope. You see the fundus, and at the same time you see the same image, but this image is about in thickness, the resolution of the confocal microscope applied to the eye, while this one is producing an image with the thickness of 3 microns. And because the eye is curved, the back of the eye is curved, when you do a cut, a constant cut, you will get a very thin layer, and this thickness is only 3 microns. That's why you start seeing in unfast orientation, in constant depth orientation, you see the layers in depth. All these layers which I labeled before, ganglion cell layer, outer nuclear layer, all these are now seen in an unfast cut, because the technology has the capability of producing so thin images. Applying the technology to the anterior chamber, again you see the cornea, the iris is here, and there are instruments now dedicated for either the anterior segment or the posterior segment. Or if you do a magnification, you see nerves in the cornea. So that is axial, that's lateral. These are images which have an axial resolution of around 10 microns. And there is technology now to provide that 5-7 microns commercial. More about the technology I presented here, you can find it in this review in Journal of Microscopy, which is open access. If you go to Journal of Microscopy and you write my name, you should be able to find it and get the PDF explaining the technology and applications. So now more on the technology. So far we discussed about interferometry principles, low coherence interferometry, adding scanning in top of that, producing an optical coherence tomograph. Now let's dwell more on the technology of OCT. So what do we need to build a tomograph? You need this interferometer, I already alluded. To get good image, you also need an interface optics, and for the eye we use a chin rest, or for microscopy we use a specialized confocal microscope. And you need here to add a pinhole to reject the off-axis rays, and the broadband source. So that was what I have explained so far. That was the principle of time domain, and the larger the band is, the better the axial resolution. However, the evolution of technology didn't stop here. We replaced this source without doing anything else. No change, absolutely no change, apart from the fact that the photodetector here has to have larger bandwidth. If you replace that with a tunable laser, and I'm going to explain how that works, you obtain the same thing as before with advantages and disadvantages. And I would like to refer to those both advantages and disadvantages. But this is the most preferred technology now, which now there is already a company selling instruments for eye examination using a tunable laser. And another modality of this modern technology is this one. We replace the tunable laser, we replace the photodetector, we put the broadband source back, and here we have a spectrometer. And this sketch and the previous sketch of the tunable laser, you may see them differently, but in fact they represent the same technology, which is you interrogate the spectrum at the interferometer output here with a device. This device will tell you how the spectrum looks like at the interferometer output. So here we interrogate that with a spectrometer, while in the previous technology we used a tunable laser. There is a fundamental difference between this, which I'm trying to explain, that the old technology, time domain, as I explained, those wave trains superposed, you obtain that superposition only when the that length was equal with the other length, i.e. the difference of this and this, we'll call it optical path difference. So when the optical path difference was 0, i.e. this length match the length of the other one, you obtain signal. So time domain will work around this position. However, in spectral domain, the other two technologies, you have to sit away, and ophthalmologists know when they use this, because they take the chin rest slightly away from the eye to avoid a problem, which I'm going to present now, not to see the image reverted. They take the eye away from the optical path difference and work over a range of several millimeters of optical path difference. So how this tunable principle works? So let's take an interferometer, and if you look with a spectrometer at the interferometer output, let's say that the difference between the beam splitter, the distance up to the object mirror, and the distance from the beam splitter to the reference mirror is about 30 microns, so the coherence length was 10 microns. In that case, the spectrum, if you use a spectrum analyzer, will be this. That's the way it looks. If you take now a very thin laser in wavelengths, this is exactly how thin it is in spectrum, and you shift it along, in time, you generate a signal. So you can read it. You read it by practically scrolling the spectrum with a very thin, narrow band laser. So that's the way we interrogate the spectrum. That's the way we read the modulation in the spectrum. Let's say now that you have another scattering center in the eye, in the tissue, in the skin, which is at a larger distance. At a larger distance, let's say not 30 microns, 80 microns, 8 coherence lengths. There will be more peaks here. There will be more peaks. So now if I do again the scanning in frequency, in optical frequency, I'll get in time this. So that's a simple way in which I can translate the modulation from the spectrum into a time signal. And by reading the number of peaks here, I could practically decode the distance where the optical center is. So I can decode and find out where that scattering center was. So if we make now a comparison in between either spectrometer based, where we use a spectrometer, and that is swept source tunable laser, what determines the depth resolution? The depth resolution in both cases will be again the bandwidth. But like in time domain, is how large is the bandwidth, how many colors you put there, while in the tuning modality is the tuning bandwidth. Now, there is another limitation which when I explained the way time domain works, I told you that that sketch explains both time domain and spectral domain in terms of the range. Because it's this idea of phase relation between the waves. Now, what you need for interference, you need waves which carry the same relation in between the object and the reference. And if you delay too much, you lose that phase relation. So practically the axial scan range is limited by the coherence length of your optical source here in the tunable laser, and you can make an association with the coherence length of the wave coming from the spectrometer. It's the spectrometer now which diffracts the waves, and that creates now an equivalent. Practically by diffraction we increase the coherence length, the physicists will know, but it's the same limitation practically. It's the coherence length of the waves interfering in both spectral domain technologies. And people knew that even before the advent of OCT. People used tuning, but tuning was limited in sensing and telecom to very tiny bandwidths, to very slow tuning rates, and it was only the OCT community which in the last 10 years put so much work in developing this beautiful technology of tuning lasers. This tunable laser didn't exist before. They've been invented by those doing OCT. A little bit about the source. The source is an essential element of any optical coherence tomograph. So if you do a Google, you look on web pages, if you want to buy broadband sources, you'll find these companies. You can get superluminescent diodes, you can get groups of superluminescent diodes, tons of our lasers, and the technology which offers the largest bandwidth is that of supercontinuum, is called, and you can find that. So in one fiber you can have now light from blue going over 2.4 micron in one fiber. Technology which didn't exist 10 years ago. And that is one of the example of the technology coming supercontinuum sources. So, and they are all now being used in all types of application, not only OCT, endoscopy, but also in instrumentation. You see the boundaries here. So it's interesting that we performing research, we now contribute to connect two quite recent technologies. One is OCT, invented in 1991, and the other one is the supercontinuum invented in 1999. So these are the technologies which OCT research groups are putting together. Another technology is that of tunable lasers. So a tunable laser, a typical way to produce a typical laser is to take a ring laser with an amplifier, okay? So the wave goes around. You have here a tuning filter. So as you tune the filter, you can select the waves. And that is technology now being used in by several companies. You can buy this laser, they are small, and you can do research with them. Let me give you an example of research being done to produce lasers for OCT. So, group of lasers, because no laser would have the bandwidth necessary to achieve sufficient axial resolution as required for OCT investigation. We had an European Dr. Marie Curie, collaborations with multiple photonics, and produce a broadband source and interrogating the spectrum using a camera, an in-glass camera. And this is the collaboration. So we targeted these wavelengths. So for these wavelengths, why is this wavelength? This wavelength is very good for imaging the retina. There have been many curves presented yesterday by Professor Lichi, and one of them was absorption of water, and you see it here. So mainly OCT evolved for imaging retina in this range of 750 to 900. That's where time domain started. However, we know that the longer the wavelengths, less is the scattering, so we may get better penetration. And indeed, those doing ophthalmology, they are very much interested in seeing deeper and deeper, especially in layers in the retina called the choroid. So to penetrate there, we need more penetration, and the only way is by going to longer wavelengths. But if you go to longer wavelengths, the eye ball is 2 centimeters, it's water, 2 centimeters one way, 2 centimeters the other way, you have to encounter 4 centimeters of water. So because of that, the nature gave us only this chance to work in this deep water absorption, which is about 1060 nanometers. So it's here where the loss is acceptable in comparison with the conventional wavelengths. And that's what we did, is to neodymium duct fiber and ytterbium duct fiber, we put it together, and we produced a bandwidth which gave us an axial resolution of 7 microns. So you can compare here images in the eye, especially here, as you see deeper in the choroid. If you use these wavelengths, only because you change the wavelengths, you see slightly deeper. So you see more here by changing the wavelengths. And now this is an example of our work on broadband sources, and there is already a commercial company selling tunable laser systems, but working at 1050, i.e. putting together both this fantastic fast spectral domain modality together with the penetration depths allowed by the wavelengths of 1 micron. And here more is our old technology of time domain producing SLO and OCT, SLO and OCT, scanning laser ophthalmoscope OCT. And again, you can compare here the penetration depths much better here than here. Let me now go more into the modern technology, which is these two. I have already alluded to this. Let's review them again. So, you have an interferometer. So from the source, sample back. From the source, reference back. So the two waves go in this fiber, and they superpose the two waves, and now we display the spectrum of interference with a lens and a diffraction grating. Diffraction grating, lens, and the camera. So you have here the spectrum. That modulation which I presented before will be here, over the camera. So you read it, so you have that modulation, you read it, and and you see how many peaks are in the spectrum. So from that number of peaks, you know what the mirror is. If you have several mirrors here, like in tissue, you have several scattering centers, there will be a superposition of those modulations, which will come up here. The other technology, sub-source technology, the same interferometer, but we read the spectrum at the output. So from the source we go sample back, from the source we go to reference and back. So here we superpose those two, and we have two photodetectors here, balance detection, and again we read the same spectrum which is displayed here, we have it into these two fibers. Now, I'm presenting here images from skin. So this is the new technology, the spectral domain. This was obtained with a 10-50 nanometer subsource skin. You see this sweat ducts here to connect in connect in the stratum corneum, is the epidermis. You see the sweat ducts, and that is recent. Please have a look at this image and compare it with the next one. The next one is time domain. Do you think that they are very different? In terms of the penetration, they are the same. So from time to time you see the sweat duct. So that was by 2000. What I presented to you was from last year. It's more than 10 years evolution. Why the users and why the OCT researchers prefer to work with a tunable laser instead of doing it in time domain with a broadband source and moving the reference mirror? Because if you look at these two examples, they are similar. So what is the catch? What is the demand? What exactly is the element determining the choice? Okay? So in terms of the penetration is similar. In terms of the axial resolution is similar. Okay? If you play with the numbers. So what is the difference? The difference is in a disadvantage allowed by the spectral domain, which is speculated by the main users of OCT. So practically the domination of applications of being oriented to the eye determine the choice. And the choice was spectral domain because it goes faster. It goes faster. So, and because it goes faster, we can get stabler images from a moving organ like the eye, which microseconds will go as fast as tens of microseconds.